Hello friends, let's have a look at the daily challenge problem, maximum absolute sum of any subarray. In this video, we are going to explain how to apply Kadane's algorithm to this problem. And hopefully you can practice thinking in an abstract fashion. So personally, I guess this problem is a very good problem to explain Kadane's algorithm. First, I'm going to write a solution that has a space complexity On. So here space n means the length of the norms. So let me write here the list. So then I'll first write like this. Then I'm going to write a solution with O1 space. So the time complexity will be linear, that is O of n. So that's our overall plan. And this problem and the strategy or the video is similar than the previous video, right? We also take the same procedure. First, write a solution with On space complexity, and then we improve it to O1 time complexity. So let's quickly look at the problem statement. So here we are given an array called norms containing integers. So the absolute sum of a subarray, meaning the absolute value of the sum, right? So we want to return the maximum absolute sum of any possibly empty subarray. So here actually, if you look at example 1, so the output is 5. So you can look at 2 and 3. And if you look at the second example, so it's actually, for example, 8. So the sum of this subarray is -8, but we consider absolute value, that is 8. So the constraints are the following. First, the length can be as long as 10 to the power 5. So this gives us the problem size. And this 10 to the power 5 actually is a decent large number. So in leetcode, you need to think of time complexity. So here we are going to solve this problem in On time complexity. So this is basically tells that there's 0, there's positive numbers, there are negative numbers in the array. All are possible. So with that said, we are ready to look at coding. So I'm not going to walk through an example here. And then we just want to explain the Kadane's algorithm in the coding. So here the main observation is that so we can, for each position, or for each index, I, so we find the maximum subarray sum and mean subarray sum, right? Then we take absolute value of this maximum subarray sums and the mean subarray sums across all the indices. Then the result will be the one we are going to request, right? So now let me first write a solution version v1. So let's use this as preparation. So we have the length. Now I'm going to define a toList. Large, that will be going to be n times 0 times m. So similarly, actually small will be 0 times n. So here let me explain the interpretation. So here large I, meaning the maximum subarray sum ending at index I. Right, we require that the subarrays must end at the current elements at the index I. So this way of interpretation actually is very convenient. So for sure you can say maximum subarray up to. This is another interpretation. Similarly, you can interpret small. Small will be the let me copy this line here and copy this annotation here, and then I'm going to change this small I is the mean subarray sum ending at index I. So this way, actually, we can set this DP list, and then we do the return. So here, what we want to do is like this. First, I'm going to set large 0 equals small 0 equals nums 0, right? Because it's just one element, so we just use that element itself. So the result will be at least the absolute value of say num0, right? So this is actually dealing with the index 0. So now for I in range, so 1 to n. So let's set large I and small I. So let me isolate this number. Let's see this number. So we consider if it's positive or negative, and also we consider the previous one, right? So here the DP update rule will be the following. Let's first define small, right? Small will be y if small I minus 1 is greater than 0, right? So because if ending at I minus 1, so the sum is larger than 0, then if we add that to y, it will be larger. So we want to find the smallest one. So this at I will be the number itself. The reason is on the other hand, we need to find the smallest. On the other hand, we need this subarray ending at this number. So we can only choose y. Otherwise, so if the previous one, small I minus 1, is less than or equal to 0, then we can do y plus small I minus 1. And because adding this part will make the number smaller, at most equal, right? So that's this part. So similarly, we can do large I. So this large I will be y if large I minus 1 is less than 0, right? So because we require this ending at this y, but if this is less than 0, so we adding them, it will make this whole thing smaller. Otherwise, if large at I minus 1 is greater than or equal to 0, then we can do y plus large I minus 1. So then each time we're going to update this result, its previous state, then the final maximum absolute sum can only appear like this among these three, right? Small I, and this is the one, and absolute value of large I, right? So finally, after this for loop, we just need to return the result state. So this is the one way of doing this. So the way we compute this large sequence and the small sequence actually is nothing but Kadane's algorithm. So now let me first run it to test. Yeah, it passes the two test cases. Now let's look at the generic case. Yeah, it passes all the generic cases. So that's one solution. So actually, if you, this is the first time you hear of Kadane's algorithm, you can print out this large and print out this small in order to have a feeling, right? So this is the large, this is small, right? For this for case 2, then the largest absolute value will be 8, right? That's the return in example 2. So I guess this will be sufficient for version v1. So let me copy this part. So I'm going to change this one to be version v1. So needless to say, for this version, the space complexity will be O of n due to the introduction of the large and small lists. So now let's try to write a solution using O1 space. So this is our goal here. So for this, let me first initialize a result, because we are considering absolute value. So the minimal possibility is 0 here, right? So then I can make a previous large, previous small. So I can set them to be 0, 0. Before I look at the numbers in nums. So now I'm going to iterate, but I'm going to absorb the 0 into the for loop. So basically for y in nums. Notice that we don't care about the index now, right? So now let's get the current large. The current large, because we think of this large I, right? We want this ending at this current y. The current large will be y if previous large is less than 0. Otherwise, so it was going to be y plus previous large. We can do the same for current introduce a current small. It's going to be y if press small is greater than 0. Otherwise, we can have y plus press small, right? So this actually corresponds to this 2 or 3 lines. So now we need to update the result. The result will be its previous state, and then absolute value of current large, and the absolute value of ABS of current small, right? So after this, we need to reset the previous large and previous small to be current large, current small, right? So finally, we just need to return the result. So actually, this code is logically is identical to the first version, but the space complexity is improved. So now let's look at the running. You see, it passes the 2 test cases. So now, it passes all the generic cases. So here, I guess that's about it for the coding part of this problem. So my suggestion for you is that if you are not very familiar with Kadane's algorithm, you can first write a solution using version v1. So this way you can get the tool list, and then you can actually delve deeper into what's happening on each step in the iteration. So if you are very familiar with Kadane's algorithm, actually you can directly come up with this solution. Actually, this is not very long, right? So this is just some initialization. That's this 4 lines are the key logic. So with that said, I guess that's about it for the current video. If you found this video useful, you're welcome to share with your friends or classmates. Hopefully this video or our channel will encourage more practice of coding.